Hello again, everybody. Welcome back. This example 810 it's marked as a conceptual example, and so we're not going to actually plug in any values in, but we are going to solve it using general terms. Here we have a golfer who has hit a golf ball and badly misjudged the amount of friction acting on it, and it only goes a quarter of the distance to the hole. Of course, being a good golfer, he wants it to go into the hole, so we want to know how much velocity he should apply to it so that it actually does make it all the way to the hole. Maybe it barely gets there and then stops and then just kind of falls in, but the ending energy, that is the final energy of the ball, is going to be the same. The energy final here equals 0 joules, and the final energy here equals 0 as well. So the good thing about this problem is the fact that it doesn't involve any up or down. There's no height change, and so there's no potential energy that we have to deal with. So we're simply dealing with the initial energy of the ball, energy initial here, and energy initial here, and the work that is done to take energy out of the ball, which in this case, all along here, non-conservative work is done by friction. All right, I'll put a plus there. Non-conservative work is done by friction. So the initial energy plus the non-conservative work results in the final energy being 0. Same thing is true right here. All right, so we want to find what the velocity of the ball has to be in the second try in order for it to get all the way to the hole before coming to rest. Okay, so we're not going to actually use any numbers, but we are going to use some general terms right here. So let's first of all take this and shrink this down a little bit. All right, so we have a little more space to work with. I'm going to move it up like that. Is that not the best place for it? Maybe here. We'll try that. Okay. So let's say right here. I'm going to redraw this right here. The initial kinetic energy, the terrible E, equals 1/2 mass times the initial velocity squared, right? MVI squared. And that's the velocity that only gets the ball a quarter of the way to the hole. So here's the ball right here. Final energy of the ball is, not final velocity, final energy, sorry. Energy final of the ball equals 0, which means the non-conservative work that was done from there to there, the non-conservative work must have been done by friction. All right, now what's the friction of the ball? All right, well it's mu k times mg. Of course, we don't know the mass of the ball, right? But we're simply going to call it the friction force Fk. Since we don't know, let me fix that K and the F. Since we don't know the coefficient of kinetic friction, we don't even know the mass of the ball, we're just going to call it Fk times our distance right there. Okay, now of course, and I probably should have written this in there ahead of time, friction always acts how? It always acts negatively, right? Against our system, so it really should be negative Fk times our distance. We're not worrying about the mu k or the mass of the ball. We're just going to call it the friction force times the distance, and of course it always acts against. In the second part, it goes much further. Well, I'm going to just draw it. I should have drawn the first one going shorter, only like right here, right? But I would have run out of space. Oh, heck with it. I will draw it further. So from here to there, the final energy is 0, just like I drew up above. Right there, okay. And the initial energy of the ball, energy initial, equals 1/2 mv initial squared. We'll call this A. So try A and try B. Sorry if I'm having trouble drawing over on the side. It's because there's a menu that kind of gets in my way. Try B right there. So I'm going to call that V initial B and V initial A. Okay. And in between here and here, we have a loss of energy, right? Because friction is acting against. So between here and here, there's non-conservative work that is done. So that is minus, right? It's negative. It's friction. Friction was acting against. Times Fk times now 4d, 4 times the distance as the original putt. Okay? So let's see if we can let's make a statement about the initial velocity for the first putt and then see how the second initial velocity should compare to it. Okay, so for A, right here, we're going to say energy initial plus the non-conservative work equals energy final. All right, well, energy final is 0. So that means the initial energy has to equal the negative non-conservative work, and negative work is just going to be the non-conservative work. All right, Fk times the distance. All right, so energy initial, what kind of energy does it have initially coming off the putter right here? Well, it doesn't have potential energy. There's no up or down or anything, so it's all going to be kinetic. So 1/2 mv initial squared equals the non-conservative work that is done. That is Fk times d. Fk times the distance right there. All right, well, let's rearrange and solve for our initial velocity. Let's see, the m is going to be divided down, and then the 2 is going to be divided up right here. So that means the initial velocity for part A is going to be 2 times the friction force times the distance divided by m, and of course, to get rid of that that square right there, we're going to square root it. All right. Let's compare that now with part B. With part B, where he has to hit it 4 times the distance, and friction is acting against that moving ball for 4 times the distance. Well, it's still true that the initial energy plus the non-conservative work equals a final energy, and of course that's going to be 0. All right. So as we did in the previous part A, we concluded that the initial energy is going to be equal to the non-conservative work that is done. Well, the initial energy, once again, is 1/2 mass times velocity initial squared. I'm going to call it initial velocity B, put a little B right there. I should have put an A next to this guy. B, because we're in part B. And equals, what? What's our non-conservative work that is done? Well, it's a friction force, Fk, times 4 times the distance now, right? Fk times 4d, times 4d right there. All right, well, once again, we're going to solve for that initial velocity right here and see how this compares to the initial velocity for part A. Once again, this 2 is going to get multiplied up. The m is going to be divided down. So it's going to be velocity initial for putt B is going to be 2 times, I'm going to put the 4 out front, and I'll tell you why in just a minute. Actually, I'll put the 4 all the way out front. 4 times 2 times kinetic friction force times the distance divided by m. All right? But of course, that initial velocity was squared, and so to unsquare that, we have to square root it, which means we square root both sides. Which means I'm going to do this. I'm going to take square root that and square root this right here. The reason I did it this way is because all this is the exact same thing as that. And the only difference is that we have this square root of 4 out front. So we can really say, since this is really describing the initial velocity for putt A, we can say the initial velocity for B equals the square root of 4 times the initial velocity for A. which means that this ball is gonna get all the way to the cup before stopping, or just barely getting to the edge of the rim before stopping, then that means initial velocity for putt B has to be, what's the square root of 4? That's 2, right? That's the square root 2. So you have to hit it twice as hard for putt B in order to get it to the cup. So it's going 4 times the distance, but remember, with kinetic energy, velocity is squared, and so if you double your velocity, you're really putting 4 times the energy into the putt, which means it can resist 4 times the non-conservative work done by friction. Okay, so this is another application of conservation of energy dealing with non-conservative forces. As long as we account for that non-conservative force, it should make sense, and we have all of our energy accounted for. So, thank you for following along. If you have any questions, please make sure you see me, and I'll see you on the next one.